Hey everybody, it's Miss Miller again here to teach you Chapter 4, Section 4. I've split it into two videos for us, focusing first on solving exponential equations. So let's get started. The topics in this section are solving exponential equations with and without logarithms, solving exponential equations using your natural log and using your natural base, solving exponential equations to solve real-world problems. The next video is going to talk about solving logarithmic equations with and without your natural log and natural base, and using your properties, not just the additive property, but also your quotient property and power property. I should probably change that, but all of your properties to solve logarithms. There's practice in Delta Math for you to do for both of these topics, and you have 2 days to get it done. As always, email me with any questions. So we're going to start off easy. If we look at this, we have 3 to the x minus 1 power equals 81. Now, there's 2 methods of solving this. The way I want you to look at this is that there's a relationship between the base of 3 and the base, technically, of 81. 3 to the power of something does give us 81. So we can rewrite this so that our equal sign is now being used as equivalents, so that we can just compare our exponents instead of having to actually solve using the inverse of exponential, which is logarithms. So I typed out some hints here that might help us. Which that best describes this expression? Well, 3 to the x minus 1 equals 4, not so much. X minus 1 equals 4, not going to use that. 3 to the x minus 1 equals 3 to the 4th. Well, we have something here because 3 to the 4th is 81. So I'm going to first use this step. So I have 3 to the x minus 1 power equals 3 to the 4th. Again, how I figured that out was 81 is 3 to the 4th power. Now you could also say 9 squared, but that's not going to really help us here when we're trying to have the same base. Now, again, think of an equal sign as equivalence. So 3 to the x minus 1 is the same as saying 3 to the 4th. Well, how can I figure out an x value that gives us the same power? So what you can do is just take your exponent and set them equal to each other, which is right here. So we have x minus 1, which is my exponent, equals 4. Add 1, and I get that x equals 5. It's a little number manipulation. All right, we can take a look at this as well. If we look, 4 to the x plus 1 equals 32. Does 4 and 32 share a common base? Well, 4 squared gives me 16. 4 to the 3rd is 64. So they're not necessarily related, but 4 can be made smaller. I could rewrite 4 to be 2 squared, and then the x plus 1 is still in my exponent. Equals, and 32 could be written as 2 to the 5th. Now we have the same base. So if we take a look, I have 2 times x plus 1 equals 5, now that I have the same base. You can do this in multiple ways, but if we distribute, you get 2x plus 2 equals 5. Subtract 2. 2x equals 3. And oh, we might get a fraction as an answer. Don't be afraid of that. Please leave it as the exact 3 over 2, not 3 over 3. All right. If you have any questions, let me know. Now, this is a very similar problem. However, if you look at it, 4 and 15 do not have a common base. 15 cannot be rewritten in any exponential form besides itself, 15 to the 1st. So how might we solve this? Well, if we solve something like x plus 1 equals 2, we do the inverse. So here, to do the inverse of an exponential, we're going to use our logarithmic property. So if I remember correctly, one of my properties is that the log base b of b to the x gives me x. So to get x out of the exponent, I can take the log with base 4 of x. So I'm going to take log with base 4, 4 to the x power, equals log base 4 of 15. Log with base 4 is just an operation. Knowing that it equals x, I now get x equals log with base 4 of 15. This is where we now need to use our change of base formula. Our change of base formula, as you may recall from our last video, is log b of m equals log of m over log of b. And you could also do natural log. So to evaluate, I get x equals, now this is your exact answer, log with base 4 of 15. But when we want the decimal approximation, we're going to write log of 15 divided by log of 4. And when we calculate that, now notice this is two separate logarithms. So make sure you're using your parentheses correctly, and you should get 1.953. Depending on how the problem asks, I always go with 3 decimal places, but that's up to you. All right. Now, remember that a common log is something that has a base 10, which makes life pretty easy here, that if I just take the common log, or just log of 10 to the x, and take the log of 8,000, I'm going to get log is a common log, so I get log base 10 of 10 to the x gives us x. And in my calculator, I can evaluate log of 8,000, which gives me 3.903. Pretty straightforward. Now, when we look here, sometimes we need to do a double log because we don't have something similar. 3 and 7 definitely don't have the same base. So what I'm going to do is use my power property of logarithms and take the log. Now you could also do natural log of 3 to the 2x minus 1 power equals log 7 to the x plus 1 power. My power property allows me to pull 2x minus 1 times the log of 3 equals plus 1 times the log of 7. Well, log of 3 is just a number. When I take the log of 3, I get 0. I'm going to put it 0.477 equals, sorry, there's 2x minus 1 in front. And I have x plus 1. And the log of 7 is going to give me 0.845. And now this is back down to an Algebra 1 equation. You can distribute, you can divide. It's up to you with what you want to do. I'm going to distribute, so 0.477 times 2 gives me 0.954x minus 0.477 equals 0.845x plus 0.845. And now we're just going to solve. Moving my x over, I have 0.109x equals 1.322 divide by 0.109, and I'm going to get x equals 12.12 All right, as I promised, we're going to take a look at things with your natural base. Your natural base of E, we know that to be 2.178, or 2.71, sorry, 2.718. If we take a look at this, in order to solve this, instead of using a common log, we want to make sure we use our natural log, remembering that the natural log of e to the x equals x as one of our properties. So if I keep the natural log of e to the x, I have to do it to the same side, so I keep the natural log of 9. This gives me x equals the natural log of 9, and my calculator shows that the natural log of 9 is about 2.197. So that's what we're going to say x is. Which kind of makes sense because e is less than 3 but more than 2. And we know that 3 squared is 9 and 2 to the third is 8. And so we kind of have an idea of where, if a number is between 2 and 3, what that exponent should be. When you're solving, make sure that you isolate e to the x first. Otherwise, you're going to have to expand and condense, which makes it a little more complicated. So I'm going to divide by 4. 4 does not go into 91 evenly, so we're just going to leave it as my favorite F word, fraction. And now I'm going to take the natural log of e to the x to both sides. Natural log of 91 over 4. Remembering that this is one logarithm, so it'll be the natural log, and in my calculator, I'm going to put 91 divided by 4. I'm not going to do natural log of 91 divided by the natural log of 4. We just put it all in as one logarithm. So I end up with x equaling 3.12, and I'm going to round up for the third decimal place, 5. The next problem, same thing. We're going to isolate e to the x. So I subtract 14. I get 3 e to the x equals -3. Divide by 3. And I'm wondering if anyone has an idea of why this might cause us some issues. So I'll give you a minute to look at this. And I want you to think about the graph of e to the x. E to the x is a growth function, and we know it has a horizontal asymptote at 0. We know that exponential functions can never have a range below 0 unless it's been shifted. So this actually is no solution. And if you pay close attention, if you didn't see that right away, and you did the natural log of -1, you get domain error. Because it is no solution. It is not possible. All right. If you take a look at this, it might be a little difficult to isolate e to the x because there's 2 of them. If we take a look closer, this is actually something we call quadratic form. Remember U substitution. So if we take a look and I see that I have 2 times x and I have 1x, that I could do U substitution to be e to the x. So I could say e to the x squared minus 5 times e to the x plus 6 equals 0. If I plug in u, I now have u squared minus 5u plus 6 equals 0. I can factor this to be u minus 3, u minus 2 equals 0. So u equals 3 and u equals 2. However, that's not my final answer. I need to plug back in e to the x. E to the x equals 3, e to the x equals 2. I can take the natural log of both sides, so I get x equals the natural log of 3, and x equals the natural log of 2. By taking my natural log of both sides, and as a decimal approximation, my natural log of 3 is going to give me 1.09, and we'll round up to say 99. And our natural log of 2 is going to give us 0.693. So here is when you get two separate answers for x. Be careful to make sure that your x values are never going to give you a negative answer, because that wouldn't work in the top. So always just double check that it fits the equation. All right, last problem. Applications. How long will it take $25,000 to grow to $500,000 at 9% annual interest compounded monthly? So this goes back to our compound interest problems, where we take what our account balance starts with, our principal, right, times 1 plus your rate as a decimal over the number of times compounded. So the number of times compounded times t equals the amount in your account. So we have 500,000 equals 25,000 times 1 plus 0.09 over 12, because compounded monthly is 12. So the 12 t. Well, this looks like a lot, but right now our goal is to solve for the time, how long it will take, the number of years. So here's my t. I'm going to solve for that, and we're going to have to solve like we've been with using logarithms. So first I'm going to divide by 25,000 to both sides to simplify this problem. So I get 20 equals 1 plus, and now 0.09 divided by 12 is going to give us 0.0075. So I have 1.0075. So the 12t. All I did was simplify the number. So I divided by 25,000 to both sides. I'll show the work here. Divide by 25,000. And I get 20. And I simplify my base to be 1.0075, because 0.09 divided by 12 is going to give us 0.0075, so 12t power. Now at this point is where we're going to bring in our common log, or you could use natural log, it's up to you. But I have a log of 20 equals log of 1.0075 to the 12t power. This, I can now use my power property. So I have the log of 20 equals 12t times the log of 1.0075. This is all just multiplication. 12 times t times log of 1.0075. These are just numbers. So to solve, t is going to equal the log of 20 divided by 12 times the log of 1.0075. And you can type this all in your calculator at once, or you can simplify it, but what you end up getting is approximately, it's 33.4, blah, 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 blah. So it's about 33 years. Normally, with word problems, you want to round to the nearest year. And since it's not 3.5, you could also round to 34, but most of the time we're going to use the rules of 5 or more, round up, 5 or less. Sorry, less than 5, round down. All right, this concludes our lesson on exponential equations. Please take a look at the video for logarithmic equations coming up next. Have a good one, guys.